Good morning, friends. This is Dr. Rajkumar. I am working as a professor in Self Finance Engineering College at Namakkal. So today what we are going to discuss is the very first topic in gas power cycle, that is Otto cycle in thermal engineering 1, right? So let me start with the PV diagram and TS diagram first. So to start with the PV diagram, so this is your PV diagram. So you can observe first how I am starting with the diagram. Let me start with the two vertical lines, right? This is the PV diagram. This is the TS diagram. So I am starting with two vertical lines, then I am joining these two. Actually, this is the theoretical cycle. The cycle was invented by Nicholas Otto. He is the inventor of petrol engine at the time of 18th century, right? So you can watch the name. I am naming the process like this: 1, 2, 3, 4. Again 1, 2, 3, 4. See, as far as this thermal engineering is concerned, you should know how to read this PV diagram, PV and TS diagram. So people may find it difficult in reading this PV diagram. So if you are not aware of this PV diagram, you never learn thermodynamics and thermal engineering, right? So let me tell you the simple way. That is, see, this is your PV diagram. See, when you are, so I will make a process like this. Usually, when you see like this is the simple PV diagram of a isobaric process, right? Isobaric process means constant pressure process. So the word iso means even. Say for example, isosceles triangle means two sides are equal, like that. The word iso stands for even. Bar relates the word pressure. So in that aspect, this is a constant pressure process. How you are saying this as a constant process? See, when you are reading this PV-TS diagram, you will find the two parameters. One is pressure, another one is volume. So when the arrow is moving like this, when you are going towards this direction, volume will be increasing. Likewise, when you are coming this direction, volume will be decreasing. Likewise, in case of pressure, when you are going upwards, pressure increases. When you are coming downwards, pressure decreases. This is the basic principle. Once you are knowing this, you will learn all kind of PV and TS diagram. So, as far as this diagram is concerned, there won't be any change in pressure because these are all two states. State number 1, state number 2. You may be knowing that state is nothing but a character of a system at particular point. So 1 to 2 is change of state is known as process. So when I am going towards this direction, volume increases. So pressure remains constant. So this is nothing but constant pressure expansion process because volume increases, pressure remains constant, right? So let us take another example. 1 to 2, same PV. Whereas in this case, there won't be any change in volume. There won't be any change in volume. But whereas there is an increase in pressure. So this process is known as constant volume process. Likewise, let me start with the TS diagram. So here you can see that in x-axis we have entropy, in y-axis we have a temperature. So temperature doesn't change, whereas entropy increases. So this process is known as isothermal process. As I said before, the word iso stands for even or equal. Thermal relates the word temperature. Throughout this process, there won't be any change in temperature. Temperature remains constant. So that's what the story behind this PV and TS diagram. So let us come to the PV TS diagram of a Otto cycle. Hope you will understand, I think. Right. Now let me start with the process 1 to 2. Process 1 to 2. See, I wanted to name this process. First, let me refer PV diagram. So what happened to pressure? You can see that in this diagram, you can see that pressure increases. So this is what the P1. This is what P2. That means pressure increases. Then volume decreases. So because you are coming in this direction, when you are going towards right, volume increases. When you are coming left side, volume decreases. So as far as this PV diagram, pressure increases from P1 to P2, volume decreases from V1 to V2. So when volume decreases, it will be a compression process. When volume decreases, it will be a compression process. Then coming to this 1 to 2, here you can see that there won't be any change in entropy. So coming to this TS diagram, you can see this vertical line, right? 1 to 2. Here temperature increases from T1 to T2. At the same time, there won't be any change in entropy, right? Now the process 1 to 2 is known as isentropic. As for this diagram, the process is isentropic. With reference to this one, compression. Isentropic compression. What happened to the all parameters? To start with this, pressure increases from P1 to P2. Likewise, volume decreases from V1 to V2. Volume decreases from V1 to V2. What about temperature? Temperature increases from T1 to T2, but entropy remains constant. Right? So this is what the story behind process 1 to 2. Right? So coming to the process 2 to 3. So let me start with the PV diagram. Process 2 to 3, you can see this place. 2 to 3, it is a constant. Volume process, because there won't be any change in volume, but there is an increase in pressure. With reference to this diagram, temperature increases. You can see this is T2, this is T3. So temperature increases from T2 to T3, right? At the same time, entropy also increases from S2 to S3, right? So name of the process is process 2 to 3. 2 to 3 is constant volume heat addition process. Constant volume heat addition. Process. During this process, what happened to the all parameters what we have discussed already, PV and TS, right? 2 to 3, pressure increases from P2 to P3. Here volume remains constant. Finally, we will write volume. Then temperature increases from T2 to T3, right? Then what about entropy? Entropy also increases. Entropy also increases from T1 to T4. Entropy also increases from T1 to T4, right? Then, but volume remains constant. Volume remains constant, right? So we have to find out heat supplied during this process, right? Generally the formula is mCv delta T. Qs equal to mCv delta T. So mass, specific heat at constant volume, delta T stands for during the process 2 to 3 mCv into T3 minus T2. mCv heat supplied during this process is mCv into T3 minus T2. Then coming to the process 3 to 4, right? What we have discussed already. We'll start from the PV diagram. During this process, so what is the name of, first we have to name the process 3 to 4. It is just inverse opposite to that of 1 to 2. Isentropic compression is 1 to 2. Here same isentropic expansion process. With reference to Ts, this process is termed as constant entropy process, named as isentropic process. Temperature decreases from T3 to T4. At the same time, volume increases, pressure decreases. Pressure you can find out here. Pressure decreases from P3 to P4, right? Process 3 to 4 is named as, what is that? Isentropic expansion process. Yes, because volume increases. You can find here in 3 to 4 you are going in this direction. Volume increases. When you are coming in this direction, volume decreases. So you are going towards right. So that's why isentropic expansion process. Isentropic expansion process, right? Then what happened to the pressure, temperature, volume and all? Then pressure decreases from P3 to P4. Then volume increases from V3 to V4. And temperature you can find out here, temperature decreases from T3 to T4, but entropy remains constant. That's the reason why we are naming it as isentropic process. So coming to process 4 to 1, you can see that there won't be any change in volume. That's why it is known as constant volume process. There is a decrease in pressure with reference to PV diagram. When you are coming to this, temperature decreases, at the same time entropy is also decreases. This is, you can see this is a constant volume heat rejection process. Constant volume heat rejection process. So during this process, with reference to this diagram, pressure decreases from P4 to P1, volume will write finally temperature decreases from T3 to T4. At the same time, temperature decreases from T4 to T1, and entropy is also decreases from S4 to S1, but volume remains constant. So this is the process, this is the place in which heat has been rejected. So heat rejected during this process is mass into specific heat, then these two temperature difference, T4 minus T1, MCV into T4 minus T1. So we have completed all those processes. Then we have to start with the efficiency, ideal cycle efficiency. So as you all know that work done efficiency is work done by heat supplied. So this work done can be written as ideal cycle efficiency of the Otto cycle is work done can be written as heat supplied minus heat rejected divided by heat supplied. Again in turn 1 minus QR by QS. 1 minus QR by QS. Finally this will become 1 minus QR MCV into T4 minus T1 divided by MCV into QS T3 minus T2. So you can eliminate these two. MCV. So finally this will become efficiency of the Otto cycle in terms of temperature difference is T4 minus T1 divided by T3 minus T2, right? So whereas when we are discussing problem, you will be given compression ratio. So you will not see all these temperature, you will not be knowing. See, in such cases this Otto cycle efficiency to be expressed in terms of compression ratio, right? So what is compression ratio, right? How will define compression ratio? With reference to this PV diagram, you can see that this is V1, right? This is your V2. So V2 is nothing but clearance volume. So this is your top dead center, this is your bottom dead center. So for further more clearance, let me draw a simple picture of an engine. So this is your DDC, this is your BDC. So this is your piston, this is your TDC, this is your BDC. So TDC is a place up to which the piston can travel maximum to the top. So this is the minimum distance up to which the piston can travel. So beyond this piston will not go. This is the maximum distance, this is the minimum distance. So this portion, always there will be a dead space above this top dead center, right? So this volume is known as clearance volume. So now what is compression ratio? This is the total volume. Total volume, you know, total volume is you may be knowing, right? So compression ratio is defined as total volume by clearance volume, right? Nothing but V1 by V2. So I will see in detail in the next topic. So simply you know that you just simply keep it in mind. R is compression ratio, that is V1 by V2. So up to this is sufficient for this Otto cycle, right? R is compression ratio, total volume by clearance volume. Likewise, K is expansion ratio, right? That is V4 by V3, right? So both two ratios are equal in this Otto cycle, right? So what I am going to do now is I am going to replace all this temperature with the compression ratio, right? I'll be writing T2 in terms of T1 and compression ratio, T3 in terms of T4 and compression ratio. So during this isentropic process 1 to 2, I am going to write the isentropic TV relation. Isentropic TV relation for the process 1 to 2. T2 by T1 is nothing but V1 by V2 to the power gamma minus 1. So these things you should remember. You might have studied in thermodynamics, right? This is the temperature volume relation for isentropic process. For the process particularly 1 to 2. T2 by T1 is nothing but V1 by V2 to the power gamma minus 1. So this will become T2 is nothing but T1 multiplied by V1 by V2 is nothing but R to the power gamma minus 1, right? So likewise, T3 by T4 is equal to V4 by V3 to the power gamma minus 1. So same isentropic relation for the process 3 to 4, right? So as I said before, V4 by V3 is equal to V1 by V2. Then T3 is equal to T4 multiplied by R to the power gamma minus 1. Actually K and R both are equal. That's why I have introduced compression ratio at this place, because V1 by V2 is same as V4 by V3. So finally the T3 will become like this. What I am going to do is I am using these two in 1. So otherwise let us name it as 3, 2, something like that. This is 1. I am using 2 and 3 in 1. So then finally this expression will become like this. Efficiency of the Otto cycle will become 1 minus of T4 minus T1 divided by T3. I am replacing with this relation, that is T3 is T4 times R power gamma minus 1. Likewise T2 is nothing but T1 times R power gamma minus 1, right? So what I am doing now is efficiency of the Otto cycle is 1 minus T4 minus T1 whole divided by, I am taking this R power gamma minus 1 as a common factor, then this will become T4 minus T1. So these two will get cancelled. Finally efficiency of the Otto cycle will become 1 minus 1 by R power gamma minus 1. So there is no need of temperature. See, once you know the compression ratio, you can find the value of Otto cycle, right? So hope you will understand this topic. We'll see in the next video. Thank you.